Oh, shit. I don't know how to do it. Um, I have not. Shh. I have no idea how to change it, guys. Hello. Can you cope with this today? But I'll try to have it change it today, next week. Okay. Can you see this, guys? Right. So this is the student's T distribution I talked about on Monday this week. This is the density of the student's T distribution. It has one parameter, A, which is referred to as the degree of freedom parameter. And this is the notation I use to mean that a variable x has a T distribution with a degree of freedom. A is the degree of freedom parameter, which is positive all the time. What did I do? Shit. Oh, man. Oh. Sorry, let me call. It's really, I have no idea how to. Oh. So this is what we talked about on Monday this week, and these are the commands in R for computing the density and the CDF of the student's T distribution. I'm sorry, I mean the corner visualizers are not working. I called somebody in, they will be here in a minute, okay? So this is the command for computing the density. This is the command for computing the CDF, right? And these are some properties of a T distribution. The first is the expectation equal to 0. The second is the variance is given by this formula. The third is as A approaches infinity, the T distribution approaches the standard normal variable. And the fourth is that if you have a random sample from a normal distribution, then this guy here has a T distribution with n-1 degree of freedom. Now, I know on Monday some of you looked scared because, you know, you're asking me like which properties you need to know how to prove. So you will need to prove only these. So you know what I'm saying? I mean that a tick means that you will need to know how to prove 1 and 2, but not 3 or 4, right? A tick means that you need to know how to prove 1 and 2, but not 3 or 4, right? The first is it's too bright, and the second is I tried to change something, but it's all of a sudden the student says it's too bright, and can you put the corner ones?
Right.
The light or the
lights in the lights, right?
yeah, I think so. Yeah.
lights off in this room?
I don't know. Maybe you can see some of them off, not all.
I don't know if we've got control from here. I mean, that's... We'll let the doors make it brighter on there. Give me a second.
And also, if you put the corner ones back on, corner ones are off.
Ah, then.
Oh, they're back on. Okay. Okay, thank you.
You want anything else doing?
No, it's just that it's too bright. I mean, they can't see it from.
I mean, let me...
Is that okay, guys? Now, or is it too dark?
You can set it, so...
Is that better now? No.
Change the lights and that.
Okay, thank you. Is it too dark now? Hello, I can't hear you guys. Is it too dark or is it okay? It's, all right. So these are the 4 properties I listed on Monday this week. Among the 4 properties, you will need to know how to prove 1 and 2, but not 3 or 4. Okay? I'm sorry for the delay because I had to call the technician. Right? Now, the next thing I talked about on Monday was this one here, which is an extension of the student's t-distribution to allow for mean and scale. So the mu parameter, it controls the mean, and the sigma parameter, which controls the scale. So this has 3 parameters, mu, sigma, and A. A is the degree of freedom. And this is the density of the extended t-distribution. And this is the notation I use to denote a variable that has the extended t-distribution, right? And then in R, back again in R, the commands for computing the PDF and the CDF of an extended t-distribution are this one and this one. So it's dt scale with df equal to A, mean equal to mu, sigma equal to st equal to sigma. Right? And these commands, you can only use them under a specific R package. And the name of the package is as follows. You will need to right, before using any of these 2 commands, you will need to install the package which has the name metrology, M-E-T, capital R-O-L-O-G-Y. And the commands for installing a package are as follows. As I described on Monday, these are the 2 commands for installing a package. In this case, the name of the package is this one, metrology. Okay? Right. The next thing I talked about on Monday was some properties. These are 2 properties for the extended t-distribution, namely the expectation is mu and the variance is given by this formula. Once again, you will need to know how to prove. If I ask you to prove this in an exam or coursework or whatever, you will need to know how to prove this. So when I put a tick, it means that you need to know. Right? Okay. And then I did an example on Monday, which is this one. In this example, in the final step, I use this property, which is property number 5. Remember, I mentioned 4 properties earlier. This is property number 5, which says that if you have a quotient like this, a standard normal divided by the square root of chi squared with a degree of freedom divided by a, then this quotient has a t distribution with a degree of freedom, right? So in this example, I had used this property, which is property number 5. On top of the 4 properties I listed earlier, this is property number 5, okay? All right, guys. Now the next thing I want to talk about is I want to talk about briefly about the next week. We have a computer lab sessions, right? And in I want to talk about briefly about the next week. In the next week computer lab session, you will learn how to compute the density, the CDF, and the quantile and random numbers from any specific distribution. So suppose suppose you have a variable that has PDF little f, CDF capital F, right? The quantile function is defined by this. In other words, it's the inverse function of this capital F at P. This is the definition of a quantile function. The random numbers from a specific distribution are generated like this. Right? Random numbers are generated from a specific distribution through this relationship here. So is F inverse at UI. UI are IID, are independent and identically distributed uniform random numbers on the interval 0 to 1. So the Xi that you get are random numbers from a specific distribution that has the PDF F and the CDF capital F. Now, to implement these 4 things in R, this is what you do, right? You just listen carefully. Now, to implement these 4 things, the PDF, the CDF, the quantile, and the random numbers, this is what you do. The first thing is you say D name X, right? This, if I have a red pen, here we are. This command here will compute compute the PDF, right? And here name, I will explain what name is in a minute. And if you type P, the name of the distribution, X, then this will compute the CDF, right? And if you type Q, name, P, right, this will compute the quantile function Q at P, right? And finally, you should type R and then the name of the distribution, and then you say N, right? This will generate the random numbers x1, x2, up to xn, right? All right, so you understand what I'm saying, right? So these 4 commands in R, the first command will compute the PDF at x, will compute PDF at x. And the second command will compute the CDF at x. And the third command, QName, will compute the quantile at P, and the fourth command, RName, will compute the random numbers x1 to xn, right? N is the sample size, right? And you will learn more about this next week when you come to the the lab sessions next week, right? So here, the word name means the name of the distribution. For example, if you supply the name NORM, which is normal, short for normal, these 4 commands will read as dnorm, pnorm, qnorm, and rnorm. So it will respectively compute the PDF, CDF, quantiles, and random numbers for the normal distribution, right? Right? Okay. So we will talk about that next week. But before that, I'm going to return to something I talked about at the beginning of this course. You may remember that at the first day of classes, we talked about what a population is. Do you recall these guys? I mean, on the first day of classes, I talked about these 4 different things: a population, a sample, a parameter, and an estimator, right? So you should know what these 4 things are. Okay, now the question is, how do you choose the estimator? So let's do an example, right? Suppose we want to estimate okay, suppose we want to estimate the average height of all men in Manchester, right? And obviously, in this case, the sample is, the population is, the population is all men in Manchester. right? This is the population. So it's really huge, right? So it's almost impossible to access all men living in Manchester. So what you do is you take a sample, right? So you take a sample. So suppose instead of asking everybody in Manchester, say suppose, I mean this is an ideal example, but let me say suppose all right, suppose you select 3 people at random, right? 3 men at random from Manchester, right? And you measure their height. So let's suppose let x1 denote the height of the first man, right? Let x2 denote the height of the second man, right? And let x3 denote the height of the third person. So you have three numbers, x1, x2, and x3. Now we want to estimate theta. Remember, theta is the average height of all men in Manchester, right? So how can we do that? So the question is, based on these 3 observations, all right, the possible estimator for theta. Now, you have only 3 data points, right? So one possible estimator for theta could be you add the 3 numbers and divide by 3, right? That's one possible. Any other possible? Can you guys think of other possible estimators? Another possible estimator is to do this, right? Another possible estimator is this, right? Another possible estimator right? So the thing is, there's no one way of estimating a parameter. There are possibly, I mean, many different ways of estimating the parameter, right? And the question is, which estimator is the best? I mean, among these 4 estimators I've listed, which one is the best? Well, I'm just asking a question, right? So how do you determine the question is, how do you determine the best estimator? When you have more than one, in this case we have 4 estimators, but in practice you can have not just 4, you can have 100 different estimators, right? But how do you determine the best estimator among the ones you have? So that's the thing I'm going to talk about today. And, right. Okay, to determine the best estimator, I need to introduce 2 criteria. The first criteria is known as the is known as the bias, right, and is defined as follows. This is the definition of bias. Ideally, you would like the bias to be as small as possible. Come on, guys. Could you please listen, guys? The smaller the bias, the better the estimator. Ideally, you would like the bias to be equal to 0, right? But it's not always possible. Number 2, the second criteria is known as the MSC. MSC stands for mean squared error, MSE, right? And it's defined as the expectation of theta hat minus theta squared, right? Okay. Once again, all right, the smaller the MSC, the better the estimator, right? All right, guys. So these are the two. I mean, there are other criteria, but for the purpose of this course, I will only talk about the two criteria that I just mentioned: bias and MSC, right? Come on, guys. Now, suppose you have two estimators, theta 1 hat and theta 2 hat of a parameter theta. Now, how do you choose which one is the better estimate? So, to answer that question, if this is absolute sign, okay, is less than all right, if the absolute value of the bias of theta 1 is less than the absolute value of the bias of theta 2, then you choose theta 1 as the better estimator, right? And if similarly, if the MSC of theta 1 hat is less than the MSC of theta 2 hat, then you choose theta 1 hat as the better estimator, right? Sometimes you can have conflicting results. For example, sometimes with respect to bias, theta 1 hat may be the better estimator, but with respect to MSC, theta 2 hat may be the better estimator. So in that case, you just have to say that in terms of bias, theta 1 hat is better. In terms of MSC, theta 2 hat is better. So you can have conflicting results. But this is how you decide. right? Okay, right. Now, I need to talk about some properties now. Well, not properties, some more definitions, all right? You keep quiet, please. More definitions. Now, so far I have given you two definitions, bias and MSE, right? The next definition an estimator is said to be unbiased if the bias is equal to 0. That's a good thing. I mean, if the bias is 0, that's a very good property of an estimator, right? Number 2, so the word here, the key word here is asymptotically unbiased, which means that the limit of the bias as n approaches infinity, n is a sample size, is 0, right? And number 3, an estimator is said to be consistent if the limit of the MSE as n approaches infinity is 0. So all these three properties are good properties of an estimator. Now, if a property, all these three properties, so unbiased is a good property of an estimator. Asymptotically unbiased is also a good property. Consistency is also a good property, right? Okay? Right, guys. And the next thing is I'm gonna describe some properties. Property number 1. Is the following, that is, the MSE of a estimator is equal to the variance of that estimator plus the square of the bias. Right. Number 2, if the expectation of an estimator is equal to k times theta, right, where k is a constant, right? So this is property 2. Property 3, come on guys, consistent. right, so these are three properties. Oh man. Oh, sorry. See, these are three properties of the things we learned. So the first so you will need to know the proofs of all of them, because I mean the proofs are not really difficult. If I have time, I will prove at least one of these properties. Okay. All right. Let me start by proving the first one. All right. Proof of 1. Okay. Now, so you start with the left-hand side, which is this, right? Now, I'm going to write this as follows. All right, you see what I've done. I have subtracted this and added this. Now I'm going to put a bracket around here. Now I'm going to use a plus b squared, the expansion for it, which is the expectation of you see what I've done? I have used the expansion that a plus b squared is a squared plus b squared plus 2ab, right? Now taking the expectation inside, you have this. This is the first term. The second term is this, right? And the third term is, the 2 is a constant, so you can pull it out. Right? You with me? Right? Okay. Now, this guy here, the expectation of theta hat, I mean, is a constant. It's not a random variable. Theta is not a random variable. So you can pull it outside. Okay? And this guy here, the expectation of theta hat is a constant. Theta is a constant. So you can pull this outside. Okay? So what you get is the following. You get the expectation of right? You guys with me? Right. Now, what do you know about the first term? Is the variance of theta hat. Now, what do you know about the second term? I just told you a minute ago. I just told you. What is expectation of theta minus theta? Come on, guys. I just defined, can't you see, guys? I just defined that a minute ago. Look, guys, here. Not this one, no. This one. The bias of theta hat is expectation of theta minus theta, right? So what you have here is simply bias of theta hat squared, right? Now, let's look at the third term now. If you take the expectation inside the brackets, the square brackets, you get expectation of theta hat minus the expectation of theta hat. Yeah. Now, the expectation of theta hat is the expectation of theta hat because the expectation of theta hat is a constant, right? So this guy here is equal to 0, right? Okay, so this is equal to, so we have proved, let me put it here. We have proved that the left-hand side is equal to the right-hand side, right? That's a simple proof, right? Now, the next one, property number 2. Now, if right? Hence, right? Are you with me? This is very simple proof. Do you remember the property? This property here, guys. We are asked to show that if this is the case, show that theta hat by k is unbiased. That's what I've just done, right? Are you okay with this proof? Yes? No? Right. That's property 2. Now, property 3. Property 3, the proof of, hello guys, let me know if you don't follow the proof. We know by property 1, the MSC can be decomposed as the sum of these two. So this implies that the limit all right, you with me? If you take the limit on the left-hand side, the limit equal to the limit of the right-hand side, all right? This implies that the limit right? Okay, so let me call this star, right? So it's clear because these two are non-negative terms, right? The LH right? All right, guys, so I have proved all three properties now. So I have proved the first, so is this proof clear, guys? The argument is that because this is equal to the sum of these two, and these two are non-negative, the left-hand side is equal to 0 if and only if both these are equal to 0, right? And that proves property number 3, okay? Now, you should now be able to do quiz 5, except that I haven't done any examples today. Maybe, do I have time? No. Maybe next Monday I will try to do some examples on the stuff I did today, right? Okay? So your quiz 5 can wait till next Monday, right? Hello. All right. If you have done quiz 4, can you please hand it to me now? Hello, guys. If you've done quiz 4, thank you, sir. Thank you. Thank you, ma'am. It's already there. Is it not there?
No, this one is here. Your example class is there, but on Monday it's not there.
What's your name, sir? Your surname. What's your surname?
Could be my mistake. I'm gonna check again. Could I email you again?
Just write your